Hello everyone. Thanks for coming for this crash course organized by the IISc-SIAM student chapter. A brief introduction about our chapter before we begin. So the SIAM is a Society for Industrial and Applied Mathematics. It is an organization with a mission to build cooperation between maths and other areas of science like technology through publications, research and community. So we mostly organize events which promote applied mathematics as applied to other fields, engineering and other science fields. I won't go into all of this, but so the IISc, so in India, the IISc-SIAM student chapter is present at various locations. There are many more chapters now, and IISc has one of the SIAM student chapters. So this was founded in February 2015, and we have had volunteers from different departments as well. So what do? We predominantly started out by organizing the student lecture series by PhD students or other master students as well. And it is not related to a particular field. It mostly spans different departments. So there have been people from EC departments or even in biology and mechanical departments who have given talks in our events. We have also had various faculty lecture series, faculty from India as well as abroad. So some of the other, so we have also conducted workshops and these have been crowd pullers, basically tools like computation tools involving Python, Wolfram, Julia and other computational tools that you will get to use in your research. So one of the most attractive events were these theme events which have been organized mostly during National Mathematics Day on December 22nd. Which have, so there have been multiple theme events which have been organized this way as well. So we also plan to have a newsletter in the future, and we are in the process of building a format which will stay, and we also plan to have some outreach events for colleges within to start out with colleges within Bangalore, and we also plan to have some symposium or mini conferences. So we have a few members now, and so we need more members for our executive committee. So if you are interested, please fill up. So I'll upload a feedback form at the end of the lecture. Please fill up your details, and if you are interested, we'll contact you through your email address there. So some of the perks of being a member of the IISc-SIAM student chapter is, first of all, if you if you plan to go for conferences abroad, SIAM conferences, you get some amount of remuneration which can be compensated for the registration. Registration fee is usually waived off, and you get additional remuneration for travel and other things. Also, you get to be a part of these SIAM activity groups on different on particular subjects. Suppose something like dynamical systems or probability theory or discrete probability, things like this, where you get to interact with other researchers in the same field, and that is free of cost if you are part of the SIAM student chapter as well. So so please feel free to contact us at this email address if you have any queries. Also check out our website. So let's start with the lecture for today. Today we have a set of 3 courses that we'll be having. So one each on linear algebra, basic probability and differential equations. The first of these is given by Harikrishnan. So Harikrishnan, you can actually share your presentation now. Harikrishnan is currently pursuing his PhD under the guidance of Professor Nitin Nagaraj in the Conscious Studies program at the National Institute of Advanced Studies, NIAS, which is located at the Indian Institute of Science campus. His research interests include chaos theory, inspired learning, information theory, machine learning, and signal processing. He completed his MTech in computational engineering and networking from Amrita Vishwa Vidyapeetham in Coimbatore in Tamil Nadu, and did his bachelor's degree from in ECE from Amrita Vishwa Vidyapeetham in the Amritapuri campus in Kollam, Kerala. So that's about Harikrishnan. So if you have any questions, please put them in the chat during the lecture. So whenever it seems appropriate, I'll interrupt Harikrishnan for the questions. Also, there will be a feedback form, link to a feedback form put in the chat. So please feel free to fill that up at the end of the lecture. Over to you, Harikrishnan.
Yeah, thank you, Vinay Kumar. It's actually a great opportunity, learning experience for me, and I really enjoyed preparing for the lecture. So I hope the audience also enjoy the lecture. So first and foremost, I would like to thank the faculty advisor, Professor T. Srinivas, and the current office bearers and members, Debendra Sarkar, Priyank Sain, Arun Kumar, and Vinay Kumar for giving me this opportunity. So today's topic is about the basics of linear algebra. So I will start sharing the screen. Are you able to see my screen?
Yes, it's visible.
Okay, thank you. Yeah, so today's topic is from coffee space to vector space, foundations of linear algebra. So first of all, first disclaimer I would like to give. This is a very, very introductory lecture, and so here I am trying to connect different concepts of linear algebra, and I will be using a very simple metaphor like coffee space. Like if you know how to make coffee, you can learn many things about vector space. That's a claim that I am making. So let's get started. So the first question is like, why should I learn linear algebra? If you look at our BTech curriculum, right? All the 4 years of our BE, we learn about linear time invariant systems. For example, like resistor, op-amp, RLC circuits. So what is so big thing about linear systems? If you look at linear systems, right? We can easily control them. It's easy to control them, predict their behavior, and model them. So here I have given 3 applications of linear algebra, starting from a layman's application to applications where some domain knowledge is required. The first and foremost is like the Google search engine, right? So before, when I got this opportunity, right? So I was just checking about IISc-SIAM student chapter. So you can see the links that that appeared in the search engine. Like you can see here, the first link. So now why this link came first? So for that, we need to know the mathematics behind the Google search. So if you look at the mathematics, right? So it turns out that there is linear algebra there. Like the idea of connecting one web page to another, like linking web pages. So the core of that is linear algebra and probability. So the second example I would like to give is the example in a neuroscience lab, where we often take the EEG signals. So EEG signal is actually a mixture of the brain dynamics, the heart dynamics, the breathing dynamics, the ocular movements. So now, how do you separate out the brain dynamics from the heart dynamics and other dynamics? So in order to separate that, we use some tools called principal compound analysis, independent compound analysis. So which is nothing but ultimately boils down to linear algebra. And the third example, what I would like to give is the common examples used in signal processing. Like if you are given an audio signal or a speech signal, with what all frequencies the signal is made up of. So again, it goes back to Fourier representations, and all these are nothing but linear algebra. So it turns out that linear algebra is the heart of engineering. Even though these are different applications, but there's a unifying theme that unifies all of them, and I want to learn that today. So that's my goal. So now we can see the goal of linear algebra. The central problem of linear algebra is to understand a system of linear equations. When I say understand, I have to be more precise, right? So when I say understand, I mean that what insights can I get from a system of linear equations? So here I would be talking about the raw picture, column picture, then the existence of solution. What it means to have a solution. What do you mean by AX equal to B? What is the geometrical meaning of AX equal to B? We can also look into the column space, row space, right null space, left null space, and finally, what new can we say about the linear system? So here the approach that I'm going to take is a spiral approach, where initially I will describe some of these concepts, and then we will slowly come back to the same concept, but each time when we come back, we have a different flavor to it. So we will try to interpret the same concepts from a different point of view. So the goal is connecting ideas. So we are going to connect the solution to linear system of equations from a different point of view, and we will try to understand these connections. Yeah. So let's get started. So I'll just start with a very simple 2 equations and 2 unknown. So the first equation is minus x plus y equal to 0. And second equation is 2x plus y equal to 3. So now what is the problem that we are interested in? What is the value of this unknown variables x and y that satisfies both of these equation, right? So algebraically, what we do is like we do Gaussian elimination, which is nothing but we create an augmented matrix where the entries of the matrix are coefficients of these this linear equations. So here -1 is a coefficient of x in the first equation, 1 is a coefficient of y in the second equation, 2 is a coefficient of x in the second equation, and 1 is a coefficient of y in the second equation. And this is the right hand side. Now what we are trying to do is like we are trying to make an upper triangular matrix. So we will the motivation for making upper triangular matrix will come to that. So the upper triangle matrix looks like this. For example, if you have entries like A, B, C, D. Hello.
Yeah, can you increase the size of the cursor? It is kind of difficult to see.
Oh, okay. What about now?
Still not.
Oh, I see. Okay. I don't know. So I'm using one pen here, so I don't know how to do that.
Yeah, or you can say where you are pointing so that it is more.
Oh, you're not able to see this. I'm writing something in the presentation. Are you able to see that?
What you are writing, I'm able to see, but if you point to something with that cursor, it is.
Oh, I see. Good that you mentioned. I'll try to point it, make a strong point. Okay. So here, okay, let me tell about the upper triangle matrix. So let's take A, B, C, D, E, F, G, H, I. So the goal of Gaussian elimination is to make an upper triangle matrix. So the upper triangle matrix looks like some A dash, okay, let's say A, B, C, some 0, E, F, 0, 0, some I dash. So the entries below the diagonals, right? They are zeros. So the goal is, so let's now try and make this matrix an upper triangular matrix. The first step I will do is like I'm going to multiply 2 times the first row. So here you can see the first row is changed to -2, 2. And then what I'm going to do is like I need to make this entry 0, right? So I am going to add first row with the second row. The row 2 changes to row 1 plus row 2. So here you can see that it is of the form -2, 2, 0, 3. See, now you can see the benefit of this, right? So this is of the form -2, 2, 0, 3 times xy equal to 0, 3. So here I can directly say that 3y is equal to 3 and y is equal to 1. If I get y equal to 1, I can substitute back in equation number 1. Equation number 1 is nothing but minus x plus y equal to 0. So if I substitute back, I will get y. If I substitute y equal to 1, I will get x is equal to 1. So x equal to 1 and y equal to 1 is a solution to this system of linear equations. Now, this is the common way we have learned in our 12th standard and engineering first year. But there is a beauty to it when we see the geometry of it. So let's try and understand that. What is the geometry of the system of linear equation? So let us take the first equation, minus x plus y equal to 0. So this I can rewrite it as y equal to x. So here I can have written it y equal to x. So y equal to x is nothing but equation of a line, right? Equation of a line that is passing through the origin. So here you can see this blue line. So yeah, the blue line that is passing through the origin. This is the equation of, this is the equation of this line, y equal to x. Now the second equation also I can rewrite it as y equal to minus 2x plus 3. So here the slope, this is a slope. Slope is negative and this is the y-intercept. So you can see when x is 0, here you have 3. So again, both of these lines intersect at a point, and which is nothing but the solution. Yeah, this is nothing but a solution. Minus 1, 1, 1, 1. So algebraically, we earlier showed that 1, 1 is the solution to this system of linear equation. Now geometrically, this is called a raw picture. We are showing that the two lines, right? Two lines intersects at a point 1, 1. So now there's one more picture that is called column picture. We come to that. So how do we understand the column picture, right? So again, we will take the same system of linear equation. So from both of these equations, I can take x common from both sides. So I can write it as x times column 1 that I have written it here, plus y times column 2 to get another column vector 0, 3. So let us see where is minus 1 and 2, column 1. So you can see minus 1 and 2 is here. So this is column 1. Again, 1, 1 is somewhere is in the first quadrant. So it is here. It's column 2. And I need to get 0, 3. 0, 3 is here. So here you can use the parallelogram law of vector addition, and you can get the solution, get the value of x and y. So it's very straightforward in this example, right? You can just substitute x equal to 1 and y equal to 1. You can get that. You can and you can get the 0 and 3. So minus 1 plus 1 is 0 and 2 plus 1 is 3. So it's very straightforward in this example. So this is one way of seeing the solution to a linear system of equation. Now, what more can we understand? So if we write down this in the matrix vector multiplication format, so here I have a matrix which has 2 rows and 2 columns, which has row 1 and row 2, column 1, column 2. So I call it as matrix of size 2 cross 2, and here I have a vector of 2 cross 1. So when I do this matrix multiplication, the resultant vector will has a dimension of 2 cross 1. Yeah, this is 2 cross 1. So this can also be interpreted as Ax equal to b can also be interpreted as the weighted linear combination of column vectors. Yeah, second. Yeah, weighted linear combination of columns of A. So this is another interpretation of Ax equal to b. Ax equal to b can be seen as the weighted linear combinations of columns of A. Now let us say more about understand more about this 2 equations and 2 unknowns. 1 second. Now we have something called determinant. So what does determinant means? So first let me define what exactly is that. Suppose I have a matrix A, which is of 2 cross 2, where entries A, B, C, D. Determinant is defined as determinant of A is A, D minus BC. Now this is algebraically we write it, but what it actually means? So it actually is the area of the parallelogram. So we'll understand that. So we take the column picture. So this is the column 1. What is the column 1 here? It is minus 1, 2. That is the column 1. And column 2 is what? Column 2 is 1, 1. 1, 1. Okay. Yeah. So now what is the area of this parallelogram? So we will find out that area. So let us consider a square in this case. So here, so which has a length here. Let us consider this entire rectangle, right? So we will find out the area of this rectangle, right? So this is nothing but length into breadth. So here it is. This height is 3, and this is what? 2, right? So 3 times 2. 3 times 2 minus my goal is to find the area of this parallelogram, the shaded parallelogram that I have done right now. So I need to subtract the following areas, right? Area 1, area 2, area 3, and area 4. And you know that 3 and 2 area are the same, 4 and 1 are the same. So let us compute the area of this first triangle. So here this will be 3 minus 2, this base into height, right? Half bh. So half base is 1 in this case, and height is also 1. Half base into height plus what is the area of this triangle? Area of this triangle will be base is again here it is 1 and height is 2. Okay, yeah, it will be half. Okay, just rub this half base into height times since both of them are together. Both of them, the areas are repeating, like 1 and 4 have the same area. We will multiply by 2. So it will be 6 minus, if you do it, it will be 6 minus 3 equal to 3. Now you compute the determinant for this example, for this linear system of example. So the determinant turns out to be minus 3. So the magnitude of determinant is actually nothing but the area of the parallelogram. Now this has very interesting connection to solution to a linear system of equation. Yeah. So let us try and understand the next concept called invertibility. So invertibility. So when we say a function is invertible, right? When do we say a function is invertible? The function is 1, 1 and on 2. Similarly, there is a notion for invertibility for matrices. So when do I say a matrix A is invertible, right? So when I can write A times A inverse, if I get an identity matrix, then the inverse exists, right? So to be more precise, I have to also is also equal to A inverse A. So A inverse is the inverse of A. And when does it exist? When determinant is not 0. You can see that the inverse of a matrix is defined as 1 by determinant of A times the adjoint of A. So we don't need to focus on the formula right now, but let me give the intuition first. So what happens in this? What happens when the determinant is 0?
Hello. Can I interrupt for a second?
Yeah, sure.
Determinant equal to -3 is area is minus. So what does it mean?
Oh, the negative sign, right?
Yeah.
Yeah, actually, it's a very interesting question, a very good question actually. So if you look at this representation, right, of unit vectors, right, ij, right, I is here and j cap, right? It is in the left of I, right? The direction. Right?
Yes.
So, but in this case, you can see, right, the column is so you can consider this as the x coordinate for time being, and this as a y coordinate. See here, the j cap is to the left of I, right?
Yes.
So here it is the opposite. Here you can see that the column 2 is in the right of column 1. So the direction has been changed, right? For example, I'll just take a simple example. No? The same matrix, right? You try out interchange the columns. You can, instead of minus 1 2, you can have 1 1 here and minus 1 2 here. Now you can find out determinant. In this case, it will be 2 minus of minus 1 equal to 3. Yeah. So it is important that the negative sign change means that the direction is reversed. Direction is reversed. So becomes j. It comes like j comes here and I comes. If it is of this format, then the determinant becomes negative. Are you able to understand what I'm trying to say?
Yeah, it's not just the magnitude. So direction of I and j vectors also matter.
Exactly. That's the point. Yeah.
Okay, thanks.
Yeah. Oh, yeah. So in this case, we have an inverse. We can actually compute the inverse because determinant is not 0. And remember, these are defined for square matrices. Square matrices. So now we'll go to the next example. What can we say about this particular system of linear equations? Minus x plus y equal to 0 and minus x plus y equal to 5. So let us try and understand the row and column picture first. So we will rewrite it as y equal to x, the first one. The second one, we can rewrite it as y equal to x plus 5. So look at this equation. They have the same slope. And only difference is there is an intercept, y-intercept here. There is no intercept here. So the first equation that passes through the origin. The second equation is actually parallel to the first equation, and it has a y-intercept equal to 5. Now, from the geometry, from the raw picture, it is very clear that V does not have a solution because these two parallel lines are never going to meet each other. So it's very clear from the raw picture, we does not have no solution for this particular linear system of equation. Now let us try and understand the column picture. What does the column picture tells us? So I can rewrite this as x times -1 plus y times 1 1 equal to 0 5. So where is -1 1? So -1 1 is in the third coordinate, and 1 1 is in the first coordinate. And look at this; they are actually in the same line. They're actually in the same direction. Line may not be the correct. I can say they are in the same directions. And where is 0 5? Where is 0 5? 0 5 is somewhere here, like somewhere above, like somewhere here. Now, no matter what value of x and y you give, I can never reach outside this direction, right? So any linear combination of -1 1 and 1 1 will always be along this direction, no matter what x and y I choose. So clearly you can see 0 5 is outside. 0 5 is outside this direction, outside this direction. So from the column picture also, it is very clear that we don't have a solution to this linear system of equation. Now we can again use the term we can again use elimination, and we can see the same no solution case. We can understand from elimination point of view. So again, I am trying to make it as a upper triangular matrix. So you can have I have the augmented matrix of this system here, linear system of equations. Now what I want to do is I want to make this entry 0. That's my goal, upper triangular matrix. So what I do is that I will take row 2. I will take the second row, and I'm going to subtract the first row. So you can see that the entire this row has gone to 0, right? Now if I apply the math, so we can see that -1 0 0 times x y equal to 0 5. So this is the form 0 y equal to 5. So you can see that like this is division by 0. Now there is no solution. It's a permanent breakdown of elimination in this case. Now the question here is that what can we say about the invertibility of this matrix -1 1 1 1. You can see that if I find out the determinant in this case, right? Determinant, it is -1. -1. Oh, okay. Oh, sorry. There is a -1 here. Yeah, -1 plus okay. Oh, sorry. -1. So this will be determinant is 0. So that means determinant 0 implies that there is no inverse. But now we can try and think different ways of understanding this whole scenario. Like look at this matrix A, right? -1 1 -1 1. Look at the rows. First we can look at the rows. Row 1 is equal to row 2, right? That's the first observation that we can say. Row 1 is equal to row 2, right? Now look at the columns, right? Columns of this matrix, column 1 and column 2. Column 2 is equal to -1 times column 1. So basically what I'm trying to say is that these rows and columns of this matrix are linearly dependent, right? They are linearly dependent. When they are linearly dependent, right, you can see that the determinant goes to 0. So you can take any, you can convince yourself by taking any example. Let's take a different example, like 2 4 and 1 2. Find out the determinant of this. When the determinant is 4 - 4 0. Take any linearly dependent matrix. When I say linearly dependent, either the rows the rows will be the combination of the other rows, or columns will be the linear combination of other columns. So the determinant is always 0 for a dependent matrix, and for a dependent matrix the inverse does not exist. So all these I'm talking in the case of square matrices. The inverse does not exist. So we have a nice connection like determinant of A and invertibility and linear dependence. We have a connection. Now the question you might be thinking, right? Since there is no solution for this particular scenario, so does that mean invertibility? Does invertibility always mean there is no solution? That's the first question that came to my mind. But actually that is not true. We will come to we will see that in a couple of slides. So we will take a new case. In this case, we can see the row and column picture. So here, let us write down the matrix for matrix for this particular linear system of equation, -1, -2, 1, 2 times x, y equal to 0, 0. Now let us see the raw picture. What does the first row tells us? Y equal to x, which is a straight line that is passing through the origin, right? Now what does the second row tells us? 2y equal to 2x, which is nothing but the same as the first equation, right? So it is nothing but y. So basically both of them coincides. Both the line coincides. In the sense, both of them, both the lines are the same. Basically, that's what I'm trying to mean. Both the lines are the same. Now let us see the column picture in this case. So column picture will be what? X times -1, -2 plus y times 1, 2 equal to 0, 0. So again, let us see where is -1, -2. -1, -2 is in the third quadrant. 1, 2 is in the first quadrant. And as you can clearly see that they both are on the same line. And 0, 0 is also a part of this line. So now the interesting case, right? 0, 0 is also a part of this line. That means there is a solution. So part of this direction. So now, put x is equal to 1, y equal to 1 in this case. If you put x equal to 1, y equal to 1, you can get 0, 0. Yeah. So now put x equal to 2, y equal to 2. So again, you will get 0, 0. That means, see, in this system, right, you have infinitely many solutions. If you put x equal to 1, y equal to 1, right, it will add up to, these both will add up to 0. If you put x equal to 2, y equal to 2, again, you will get 0, 0. So in this particular case, we are having infinitely many solutions because the right-hand side, right, the 0, 0 is part of this direction, is in the direction of both these vectors. So again, so here also, now let us understand this scenario by that elimination point of view. So we have this system of linear equation. We write them in the documented format. So now what I do is like, so basically I skipped one step. First of all, I will do R1 changes to 2 times R1. And then I will apply the second step. R2 changes to R2 minus R1. So I will get in this particular format. So here again, I can write 0, y equal to 0. This actually means now y can take any value. This actually means y can take any value. If y can take any, so you can substitute any value for y and get x. So it has infinitely many solution. Yeah. So now we can talk about the invertibility of this matrix. You can, as you can clearly see that, there is a very clear dependency between the rows and the columns, right? Row 2 is equal to 2 times row 1, right? This is row 2. This is row 1. Row 2 is 2 times row 1. If you look at the columns, right? Column 2 is -1 times column 1. So there is a clear linear dependency between the rows and columns of this matrix. So definitely the determinant is 0. Determinant is 0. You can convince yourself, you can do the math and you can actually convince yourself that the determinant is 0, that the inverse does not exist. But still we have infinitely many solutions because the solution lies in the same space, same direction of both these vectors. What we try to do in this particular particular point is we try to connect the solution to a linear system of equation with invertibility, with the determinant, and with linear dependency. So I will just take a pause at this moment. Do you have any questions, doubt, or suggestions so that I can incorporate and move forward? Yeah. Feel free to ask and provide any suggestions.
There are no questions in chat as such, but if anybody has questions, they can probably unmute themselves and ask now.
Is this true only for real numbers or complex numbers also?
Yeah. Actually, you can actually do the same thing for complex numbers as well. Yes.
Okay.
Yeah. So in the case of complex numbers, we call about there's something called Hermitian matrices. like conjugate. So inverse, we also take complex conjugates when we try to do inverse and all. So, but in this lecture, I'm not actually covering about complex numbers. We will be fully focusing on real numbers.
Okay.
Yeah. But it's a good question. Yeah. So I think if there are no further questions, we'll move forward. Yeah. So now I will try and define some terms so that it will be easy for me to like use these in the coming slides. So there's a first thing is a dot product. So I will first explain what exactly dot product. So I have a vector here, x vector and y vector. Now the dot product is the angle theta that is between x and y, subtended between x and y. So dot product defined as x dot y is the magnitude of, to be precise, L2 norm, magnitude of x, magnitude of y times cos theta. So what is this magnitude, right? That I will define. So suppose x has these entries, x1, x2, xn. Then this is defined as square root of x1 square, x2 square, etc. plus xn square. This is similarly y is also y1, y2, etc. yn is equal to square plus yn square. Yeah. So now, so remember, so the end of this thing is a scalar, it's a single number. No, so because this is a scalar. Y is the absolute, the magnitude, the L2 norm of y. We call this as the L2 norm. L2 norm of y. This is also a scalar, and this is cos theta. This is anyway a scalar. So dot product will gives us a scalar. And another way, one more definition is that dot product is also equal to x transpose y. So when I say x transpose y, what it means? So when I say transpose, so x by default I am taking x as a column vector, x1, x2. x3, etc. xn is a column vector. So when I say x transpose, so I'll just write it here. X transpose, it becomes a row. x1, x2, xn. So here the dimension, the size of this, sorry, not dimension, the size of this matrix will be 1 cross n. Earlier it was n cross 1. X transpose made it 1 cross n. X transpose times y, right? So this is of the form x1, x2, xn, y1, y2 is equal to. So I can, so so when I do this vector multiplication dot product, so what I am getting is x1, y1 plus x2, y2, etc. xn, yn. So this is dot product, and it will be very useful in the coming slides. So for covering this material. Then another, so now the matrix vector multiplication. The common notion of matrix vector multiplication that we learn in our school and engineering first year and all, it's like first row times first column, and which is nothing but the dot product that I have actually defined here. So it will be ax, right? Ax and by. Then row 2 times again this column xy. So cx. C goes to x and d goes to y. Yeah, dy, and you add it up. So, but in this lectures, we are mostly interested in this particular view. So a b c d times xy equal to x times the first column, x times column 1. This is column 1 plus y times column 2. Basically, what is the linear combination of linear combination of column 1 and column 2, which will give you some b, ax equal to b, some b. So now going forward, I will define some special vectors, some which are called special vectors, orthogonal vectors. First, we will talk about orthogonal vectors. So when I say orthogonal vectors, these vectors are perpendicular to each other. So let us take our normal 1, 0 and 0, 1. So they are 90-degree apart. Now, if I take the dot product between these two, what I will get is, let's take 1, 0 times 0, 1. This will be 1 times 0, 0 times 1, it will be 0. So whenever the angle between the vectors are 90-degree, the dot product is 0. And the L2 norm in this particular case, right? Let's take this vector, right? In this case, the L2 norm is actually root of 1 square plus 1 square equal to root 2. Now, what is orthonormal vectors? So when I say orthonormal vectors, they are orthogonal to they are orthogonal. At the same time, their L2 norm is 1. They have unit norm. Like if you do the math, we will get 1 by root 2 the whole square plus 1 by root 2 all square. In this case, it will be 1. Now we have something called orthogonal matrix or orthonormal matrix, right? So yeah, so they have their matrices where you can, if you take these columns, right, column 1 and column 2, they are orthogonal to each other. If you took the dot product between these two columns, right? So you can again do that. Minus 1 by root 2, 1 by root 2 times 1 by root 2, 1 by root 2. The dot product between them is 0. And at the same time, each of these columns have an L2 norm equal to 1. And interestingly, for an orthogonal matrix, the inverse and the transpose are the same. So basically, if you multiply x by x transpose, right, you are going to get identity. So for an orthogonal matrix, for an orthogonal matrix A, okay, 1 second. For orthonormal matrix, orthogonal or orthonormal matrix A, its inverse is equal to its transpose. This is only true for an orthogonal matrix. Okay, orthogonal or orthonormal matrix. Yeah. So these will be useful in our coming slides. So now let me give you another interpretation of matrix vector multiplication. This is only for square matrices, especially for intuition for matrix vector multiplication for square matrices. So I have a vector, let's say 2, 1, 2, 1. And under this matrix vector multiplication operation, the new vector is 4, 10. The new vector goes to 4, 10. So basically, one way of seeing matrix vector multiplication is like an operator now. So it actually maps. It actually maps a vector to another vector. So in the case of square matrices, the dimensions are always the same. So for example, this is a 2 cross 2, this is a 2 cross 1, 2 cross 1. So in the case of square matrices, for this particular example, it is a mapping from r power 2 to r power 2. So when I say r power 2 is a set of all vectors which has 2 elements in it. R power 2 is a mapping from r power 2 to r power 2, this particular matrix vector multiplication. And you can see there are 2 things happening, right? If you look at this image here in the right hand side, 2, 1 is actually rotated by some angle. So there is a rotation definitely happening, and there is a stretching. It has been stretched to a value. So matrix vector multiplication can be seen as a rotation plus stretching or shrinking. Okay, matrix vector multiplication can be seen as rotation plus stretching or shrinking. But there are some special vectors, right? There are some special vectors which will not change their, which will not get rotated, basically. So they are some special. So we'll talk about that. Let us take this particular example. So A times this particular vector minus 0.415 and minus 0.909. You can see that the resultant is minus 2.234 and minus 4.885, which is nothing but.
Can we show the previous slide?
Yeah, please. Yeah.
It is true for square matrix and any dimension.
Yeah, square matrix with any dimension.
Suppose if I go for a, let's say, multi-dimension vector, let's say.
Yeah.
Then also it is true.
Yeah, so basically in this particular thing, what I'm saying now, see, in general, no, we can see matrix vector if you have a rectangular matrix of size, let's say m cross n, right? And you have, let's say, here a vector of size n cross 1, and here you have the resultant will be of size m cross 1. So in general, we can say matrix vector multiplication as a mapping from r power n to r power m. So let's take an example. Let us take a 2 by 3 matrix where there are 2 rows and 3 columns. So here also we'll have 3 cross 1. Let's say x1, x2, x3. And here it will be what? It will be of size 2 cross 1. So here you can see, here the notion of rotation and stretching is not very, we cannot actually compare, because here the space is different, right? Here this is an element of r power 3 and this is an element of r power 2, right?
Yes.
So in general we can see it is a transformation. So like it's a linear transformation from r power n, from r power here in this particular example from r power 3 to r power 2. But luckily in the case of square matrices, right? In the case of square matrices, the transformation is actually limited to that space itself.
Okay.
You are not going to any other space. Like by space, what I mean, like if it is r power 2, it will always going to remain r power 2. It is never going to be in r power 3 if the matrix is of a square matrix of size 2 cross 2. Okay. So you can see it as a rotation plus stretching or shrinking. But in general, we can understand it as a mapping. It's a transformation it's a mapping from r power n to r power m. Yeah, is that clear?
Yeah.
Okay. So when I say, so as she rightly asked, we can interpret matrix vector multiplication as like rotation and stretching, but there are special vectors which will not get rotated. So that special vectors are called eigenvectors. So in this particular example, right? So if they multiply A with this vector x, and what we are getting is lambda times the same x. So here the direction is still the same. So if you look at the right, the picture I am given on the right side, right? The direction is the same. So minus 2.234 and minus 4.885. So the direction is the same as that of this particular vector. The direction is the same. Only the magnitude changes. The magnitude is either stretched or shrinking. So that is called the eigenvalue. The magnitude by which the vector is stretched or shrinked. That is the eigenvalue. And eigenvalue and eigenvector are one of the core things we need to know about core things in linear systems. If you know the eigenvalue or eigenvalue of a linear system, right, we can actually tell the system whether the system is stable or unstable. So many things we can tell about the system. We can actually predict many long-term behavior of the system. But anyway, we will not be covering all those things in this talk. It will be as a course, a part of course you will be learning all these things. Yeah, and it has applications in many fields. So one common thing is the Fourier transform that we learn in the undergraduate studies, right? The Fourier transform, we have this function called e raised to I j omega t, right? It is actually an eigen function to an LTI system. If you look at the Signals and System textbook by Simon Higgins, there's a statement like that. So like it's very, very related to what we are like studying right now. Yeah. Now let us connect. Right now my goal is to connect eigenvalue, determinant, and linear dependence or independence. Let us try and connect these ideas. So there is a lot of fun in connecting ideas. Let us take an example. Let's take an example A matrix A. Let us define it as 1, 0, 2, 3. Okay. Now first, let us find out the determinant of this particular matrix. So what is the determinant in this particular case? 3, right? It will be 3. Determinant is 3. Now let us find out the eigenvalues of this particular matrix. So now we learn how to find the eigenvalues. So we have Ax equal to lambda x, right? So remember x is a vector. So that means I can rewrite it as Ax minus lambda x equal to 0. Again, it is a vector. Remember, it is a vector. So, and I can take lambda a minus lambda I times x vector equal to 0. So when I do that, let us see what is going to happen. So a is 1, 0, 2, 3 minus lambda 0, 0, lambda. So why lambda is a diagonal? Because this is an identity matrix. I have multiplied the identity matrix by a scalar called lambda. So now I can, the resultant here, it is 1 minus lambda, 0, 2, 3 minus lambda. Now I will do the determinant of this thing, right? A minus lambda I equal to 0. I will solve for this. So when I do that, what I will get is 1 minus lambda times 3 minus lambda equal to times 2. Anyway, it is 0. So minus 2 times 0 equal to 0. So I will get 1 minus lambda times 3 minus lambda. So lambda, what is lambda and what is lambda here? So lambda can take the value 1 and 3. So 1 and 3 are the eigenvalues for this particular case. Okay. So now, if there's a determinant, if the determinant is not 0, we have eigenvalues. We have this like real eigenvalues, which is not equal to 0. Now, and we can say that clearly there is no linear dependency between the rows of this matrix A, and there is no linear dependency between the columns of this matrix A. This can be clear if you do the Gaussian elimination. You can do that. Now let me take another example. A equal to like 1, 1, 2, 2. Okay. What is the let us find out what is the determinant in this particular case. Okay, sorry. The determinant in this particular case is 2 minus 2 equal to 0. What is the eigenvalue in this? Definitely inverse does not exist because determinant is 0. What is the eigenvalue in this particular example? So let us find out that. So it will be. So I'm not going to write down the entire steps. I am going to just directly find out determinant of A minus lambda I equal to 0. So it will be 1 minus lambda times 2 minus lambda minus 2 equal to 0. Right? So if we solve for it, what will we get? So 2 minus lambda minus 2 lambda plus lambda square minus 2 equal to 0. So minus 2 plus cancelled, and we'll get lambda square minus 3 lambda equal to 0. Right? So in that I can take lambda common, lambda minus 3 equal to 0. So here you can see lambda into lambda minus 3 equal to 0. So due to lack of space, I'm going to write this entire thing here. Sorry for this horrible writing. So here one of the eigenvalues lambda is equal to 0 and lambda equal to 3. So this case is very interesting, right? Whenever the matrix A is dependent, that means either there is a row dependency or column dependency, you can see that one of the eigenvalue goes to 0. It also depends on how many rows are dependent, that we can come to later, but definitely if there is a dependency, you can see that eigenvalues goes to 0. One of the eigenvalue goes to 0. And there is another non-zero eigenvalue lambda equal to 3. So definitely, so we can see that eigenvalue is connected to determinant, is connected to linear dependence. So let us try and make it more concrete. So if you have a square matrix which is linearly dependent, then you can see that one of the eigenvalue goes to 0. Then if it is linearly dependent, then the determinant is 0. Determinant goes to 0. Invertibility does not exist. There is no inverse. And if there is no inverse, then you can have either two cases. Either you have no solution, or you can have infinitely many solution. Infinitely many solution. Two cases will arise. Yeah. If one more thing I want to highlight, if for that matrix, if the matrix is not linearly dependent, that means there is no linear dependency between the rows and columns, then determinant is not 0. Then eigenvalue, in that case, eigenvalues cannot be 0. There won't be any eigenvalue which is 0. Eigenvalue cannot be 0 if the matrix is not linearly dependent. So then the inverse exists, and then you have a unique solution. So let me go to the second iteration. So again, we will come back to the same concepts, but with a different flavor. But right now, I will just give a pause. So if you have any questions, you can ask, and if any suggestions, or let me know. Yeah.
You can unmute yourself and ask questions if you have any.
Yeah. So if there's no, yeah.
Also, I have up a link to the feedback form if you can fill that up as well.
Okay.
And Harikrishnan for 45 minutes.
Oh, I see. Okay. Yeah. Thanks for informing. Yeah. So we will go to the second iteration. Yeah. So now here we will try to understand all these things what we had learned from a different point of view, which is something called vector space. So now let us ask three people. There are three people in this room. One is a physicist, one is a computer scientist, one is a mathematician. Now, if you ask a physicist, what is a vector? What is a vector for a physicist? For a physicist, a vector is a pointed arrow with directions given by the angle and magnitude given by the length of this vector. For a computer scientist, vectors are nothing but an array of numbers, a list of numbers, and they play around with. And for a mathematician, right? Mathematician does not just say about vector. They say something called vector space. and vectors. So we will first understand what is the vector space. Vector space is a collection of objects. It can be anything. Collection of objects called vectors together with the two important properties called closed under vector addition, closed under scalar multiplication. So vectors can be anything. They're just objects in a space called vector space, which satisfies mainly two important properties called closed under vector addition and closed under scalar multiplication. And the goal right now for us is to what we mean by these two properties. We will try and understand these properties with the help of a coffee space. So here what I'm going to tell you is that if you know how to make a coffee, you can know many things about vector space. So let us try and understand these two properties. What do you mean by closed under vector addition and closed under scalar multiplication in terms of a coffee? Now let us consider a scenario where there is a machine, right? The machine will generate any kind of coffee, from the worst coffee to the best coffee. So it has some technology to do that. Now, so I took a coffee and Vinay took another coffee, and I add up these two coffees. Still I get a coffee. I will not get tea. That means still the resultant coffee is also a coffee in the coffee space. And so this is called closed under vector addition. Basically, if I add two elements in that vector space, the resultant element is also there in the vector space. Like if I add two coffees, I will get a coffee. I will not get tea or Bonvita. Still a coffee, right? So it's called closed under vector addition. Now, what is meant by closed under scalar multiplication? If I take a coffee in a cup, if I scale the cup by let's say 5 units. No, I have a larger cup. Still the coffee is the same, right? I get the same coffee. The coffee is still in that space, in the coffee space. I will not get something different. So similarly, if I take an object, if I take an element of that vector space, if I scale it by a scalar, by a real number, I will again end up in that space. I will not go outside the space, right? So these two can be understood in terms of a coffee space: closed under vector addition, closed under scalar multiplication. Remember, this is just a metaphor. So this is only for our understanding. So once we understand, we can throw away this metaphor. So now, the formal definition: a real vector space is a set or a collection of vectors together with the rules of closed under vector addition and closed under multiplication by real numbers. And this is from this definition is from this book by Gilbert Strang. It's a very good book. Yeah. So now every vector space, right? Every vector space has something called dimension. Every vector space has a number called dimension. Dimension is a number. So what is dimension? Dimension is a number of basis vectors. So now again we are introducing a new term called basis vectors. So dimension is a number of basis vectors. So now what is basis vectors? So basis vectors are the first thing. The basis vector has to satisfy two important properties. They are linearly independent. So we will come to that. What do you mean by linear independence? And basis vector should span the vector space. So two properties important for basis vectors is they are linearly independent and they should span the entire vector space. So again, we'll go back to our coffee example. So now, how do we make a coffee? What all ingredients we need to make a coffee? We need coffee powder, okay, coffee powder, milk, water, and sugar. And so we are not just pouring all these things together, right? We take a calculated measure of coffee powder. That measure is given by this number W. A calculator. We have a teaspoon. We will not take a bucket full of coffee powder, right? We will take a teaspoon of the coffee powder. So there's a calculated measure given by this W, and we take a calculated measure of milk given by X, water and sugar, calculated measure of water and sugar to get a coffee. So basically, the coffee can be seen as a linear combination of weighted linear combination of coffee powder, milk, water, sugar. So now, let us try and understand these four ingredients: coffee powder, milk, water, and sugar. Can I get sugar from the linear combination of coffee powder, milk, and water? No matter how I mix coffee powder, milk, and water, I can never get sugar. So that means, I'll come to that. So sugar can never be obtained by the linear combination of coffee powder, milk, and water. Similarly, by the linear combination of coffee powder, milk, and sugar, I will not get water. Similarly, by the linear combination of coffee powder, water, and sugar, I will not get milk. So basically, what I'm trying to say that these four ingredients, right, coffee powder, milk, water, and sugar, are linearly independent. One cannot be obtained by the linear combination of others. that's what I mean by linear independence. Basically, in our earlier matrices, we have seen linear dependency, right? We say that row 2 is 2 times row 1. That means row 2 is a 2 is nothing but 2 times a multiple of row 1. That is linearly dependent. But in this case, you can see that none of them can be obtained by the linear combination or scaling of other ingredients. So that means they span, since they are linearly independent, so and they span the entire coffee space. So coffee powder, milk, water, sugar can be seen as a basis vector that spans the entire coffee space. Now the question is, what is the dimension of this vector space? Dimension of coffee space. Since there are 4 basis vectors which are linearly independent and which spans the entire coffee space, we call this is a 4-dimensional space. So because dimension is nothing but the number of basis vectors, and basis vectors are linearly independent and span the space. So this coffee space is a 4-dimensional space. Now, in this 4-dimensional space, what if I remove water? If I remove water, I will get a subspace, which is nothing but the set of all black coffees. So there is a subspace in this 4-dimensional space, and which is, if I remove water, which is nothing but a set of all black coffees. So yeah, so now, this is my friend's horrible coffee. He gives 2 cups of coffee powder, 1 cup of milk, 4 cups of water, and 3 cups of sugar to give me a coffee, and which is horrible. And for him, this entire coffee can be represented as 2, 1, 4, 3. So 2 times coffee. So 2, 1, 4, 3 is a representation of a coffee for him. So, and this 2, 1, 4, 3 can be seen as linear combination of the Euclidean vectors, like 1, 0, 0, 1 times 0, 1, 0, 0, 4 times 0, 0, 1, 0, 3 times 0, 0, 0, 1 to give me 2, 1, 4, 3. And this is, so this is nothing but, this entire thing what we have written, right? This is nothing but w times x, w times first column, first vector, x times second vector, y times third vector is nothing but ax equal to b. Ax equal to b. In 2 dimensions, we have actually written this. We have seen that ax equal to b is nothing but a weighted linear combination of columns of A. So we have, with this coffee space, we are actually showing that. So now let us try and understand something called column space. So every matrix, right? Every matrix has something called column space. So when I say column space is a space spanned by the column vectors of A. So you can see here, I have written it in the right side. The space spanned by the column vectors of A. We write span of the columns of A. So this is a column 1, column 2, column 3, column 4. When I say span is nothing but the linear combination of column vectors, of these column vectors. So since there are 4 vectors, right? Four vectors, and you can see that all of them are independent, because I cannot get any of them by scaling or adding other components. For example, let us take this guy, right? Let us say the first column. I cannot get column 1 by adding column 2, column 3, column 4, or scaling column 1, column 2, or scaling column 2, column 3, column 4. Whatever operations you do on column 2, column 3, column 4, I will never gonna get column 1, because the first entry of all of them is 0. So in this case, right, and that is true for all of the other column 2, column 3, column 4. Like if you take column 2, I cannot get column 2 by the linear combination of column 1, column 3, and column 4. So yeah, so this is a 4-dimensional space, and they span the entire R power 4. When I say R power 4, R power 4 is a set of all vectors having 4 elements in it. So entire R power 4 can be spanned by the linear combination of these vectors, these basis vectors. Remember one more thing, basis vectors are not unique. There are infinitely many basis vectors. So I can even scale this, right? I can even have 1 by root 2, 0, 1 by root 2, 1 by root 2. This is also a valid basis vector. They will also span the entire column space. So similar to column space, we have something called row space. So row space is nothing but, now when we say row space, right, we are interested in the rows. We are taking the linear combination of all these rows. And again, for a row space, we can define the same things like dimension, basis, everything we can define. So row space, column space, and these are very, very interesting. Like Professor Gilbertstein talks about this in a greater detail. So I would recommend you to go through the material of Professor Gilbertstein. I will share those materials at the end. Yeah. Yes. So now let us do some examples, right? Now let us try and understand this problem. So we have AX equal to B. So this can be seen as linear combination of columns like W times 1, 0, 0 plus X times 0, 1, 0 times 2, 2 equal to 2, 2, 0. So this can be seen as 1, 0, 0 is what is the, let's say it's the X-axis, right? It can be seen as the X-axis. 0, 1, 0 is in the Y-axis. So the linear combination of definitely this is in a three-dimensional space. The linear combination of these two vectors, right, will span a plane. Will span a plane in the 3D space. Why it is only a plane? I will never get any value in the any value which has a third coordinate. For example, if I have 2, 2, 1, I can never get this particular vectors by the linear combination of these two vectors like 1, 0, 0 and 0, 1, 0, because you can see the last element is 0 and here the last element is 1. No matter what W and X I choose, I can never get 2, 2, 1. So this actually spans a subspace of a three-dimensional space. So now let us see what is the basis vectors of this column space. So the column space has is spanned by two vectors like 1, 0, 0 and 0, 1, 0. Since there are two basis vectors which are linearly independent and they span the entire subspace, in this example the subspace is a plane, and so we call it as a two-dimensional. It is a two-dimensional vector space in a two-dimensional vector space. The dimension of this vector space is 2. Because why it is 2? Because it has only two basis vectors. And let us see the solution. So where is 2, 2, 0 lying? 2, 2, 0 is also lying in this particular space. So now we can see, right? AX equal to B has a solution. So AX equal to B has a solution when B lies in the column space of A. Here you can see 2, 2, 0 lies in the column space. 2, 2, 0 lies in the column space of A. So here you can see 2, 2, 0, right? It lies in the column space of A, and column space is nothing but the space spanned by 1, 0, 0 and 0, 1, 0. Now, yeah, so here's some questions. I have already answered these things. Yeah. Now, what can you say about this particular scenario? 1, 2, 3 and 2, 4, 6. Can somebody want to try out what will be the answer to this particular scenario? Like, what can you say about the column space? What is the dimension of the column space? Can anybody try? Like, you can say, yeah, whatever you understand, no problem.
1. Be 1.
Wow, very good, exactly. So how it is 1? Let us try and understand that. Yeah. So if we reduce this, right, you can reduce this as W times 1, 2, 3 times X times 2, 4, 6. But 2, 4, 6 is 2. We can write 2, 4, 6 as what? 2 times 1, 2, 3, right? So yeah, so the column space is actually the span. The column space is nothing but the span of 1, 2, 3, because see, these both are actually the same, right? So definitely, as I said earlier, the basis vector is linearly independent. So 2, 4, 6 and 1, 2, 3 are not linearly independent. So definitely, I cannot choose both of them as my basis. I can only choose one. So I choose 1, 2, 3 as the basis vector. And since there is only one basis vector, the dimension of the column space is 1. And what is that? It is a line passing through the origin. It's a line passing through the origin. And you can look at this 1, 2, 3 here. Here also you have 1, 2, 3, right? So yeah. So 1, 2, 3 is also in the column space, right? So so one solution you can see is like if I put W equal to 1. And X is equal to 0, I will get 1, 2, 3. So here also again you can convince yourself that AX equal to B has a solution when B lies in the column space of A. Okay. Now, and it is again a subspace. So in this case, actually there are infinitely many solutions, right? So for example, one solution I can think is like if I give W equal to 0 and X equal to 1 by 2, again that is a solution. So in this case, you can actually find infinitely many solutions. Now, the third case, this is very interesting, right? Can you see something mysterious about the third case? Anybody want to answer? Anything mysterious about this particular case? Like you have 1, 0, 0 here, 0, 1, 0 here, and 1, 2, 3 in the right hand side. Okay, can you think in terms of solution? Does it have a solution?
No, it won't, because we can't get 3 at all anytime.
Exactly. It will not have a solution, right? So this is a scenario now. So you can see now 1, 2, 3 is, so let us understand the space, column space 1, 0, 0, 0, 1, 0. It is the normal XY plane that you see here. Yeah. So any linear combination of this 1, 0, 0 and 0, 1, 0, you will be always in this plane, You can never go outside this plane, but 1, 2, 3 is outside, right? 1, 2, 3 is outside. So it is like saying that no, I lost my key, my room key in NIAS, and I'm searching in my home. So nowhere wherever, how much ever I search in my home, I will never get the key, right? It's the same like that. My search space is limited to this particular space, and but I'm looking for a solution for something which is not there in the search space. So this has no solution. Yeah. So we have 3 cases: unique solution, infinitely many solution. So unique solution when both of these columns, right, the column vectors are linearly independent. So in the case of infinitely many solution, you can say that column vectors are linearly dependent. You can see the second column is 2 times the first column. In the case of no solution, the B thing, right? B does not lie in the column space. Yeah. So yeah. So now let us try and find. So we don't need to worry for the no solution case. We can actually find the best approximate solution, and this is very interesting. So we know that AX equal to B for the no solution case, right? It does not have a solution because since B doesn't. So this is a column space. It goes to infinity. This is a column space, and B is outside the column space, and we know that there is no solution. So AX cannot be equal to B. Now the question here is like, can I find an approximate X cap such that AX cap can approximate B? So can I find an approximate X cap such that AX cap can approximate B? So for that, let us try and see. Let us try and see how do we solve this. So if you look at this AX cap, right? What I'll do is like I will define AX cap plus some error vector equal to B, and this error vector is given by this direction. So now you can see, now I am saying that the error will be minimum when the error is orthogonal to the column vectors, 90 degree. So why is that true? Why 90 degree is important for the error to be minimum? So we can understand this by a very simple example. If you look at a line, right? If you look at a line, okay, let's have a line. I'll draw it properly. Let us take a line. And if I have a vector here, right? I'm trying. I want to find a point in this line P so that the error is minimum, which closely approximate this vector B. So now if I project it like this, okay, let's say a P dash, you can see that this distance, right? This distance is nothing but you can apply Pythogorus theorem. So this is A or B. So this distance is C square equal to A square plus B square. So C square can be minimized if C approaches close and close so that this angle become 90 degree. So when the angle is 90 degree, you have the minimum error. When this point P dash approaches towards P, right? The B also becomes closer and closer to 0. So similarly, what I'm going to say is that the error is minimum when the error is perpendicular to the column space of A. So here is the scenario. So we have A X cap plus error vector equal to B. So remember, we learned about dot product, right? So when two vectors are orthogonal, perpendicular, the dot product is 0. So here I'm saying that the column space, right? So the column space A has 2 columns, B1 and B2. Let's call it B1 and B2. So now I want to say that error is orthogonal to the column space. When I say error is orthogonal to the column space, that means error is orthogonal to all vectors in the column space. So what I am going to do is I will do A transpose times E vector. So what is A transpose? A transpose will be B1 transpose and B2 transpose. Now I can write the E vector here, right? So this I have given it here. So now you take the dot product. Dot product will be 0. Here again I get a 0. And dot product with this, I will get a 0. So now let us do the math. So ax cap plus e equal to 0. And what is e? E is b minus ax cap. Now I am saying that error is orthogonal to the column space. So I will write A transpose E equal to 0 vector. And I substitute for E. So E is b minus ax cap. So from here I'll come here, b minus ax cap. I'm substituting b minus ax cap here. Now from here I can write it as A transpose b minus A transpose A x cap equal to 0 vector. I can take A transpose b the other side, so it is of the form. So I can write, I have written it here. A transpose A x cap equal to A transpose b. X cap is equal to A transpose A whole inverse A transpose b. So basically from here, right? A transpose A A transpose A x cap equal to A transpose b vector. So I am multiplying by, I'm taking the inverse. I'm taking the inverse of this. So A transpose A whole inverse times A transpose A x cap equal to A transpose A whole inverse A transpose B. So this will be identity. So x cap is equal to A transpose A whole inverse A transpose B. Now, so we have found x cap. So ax cap, right? So what we need to find out, what is the approximate value of B, right? So ax cap approximates B. So we found one of the best x caps, x vector, right, that approximates B. So whenever you have no solution, we can apply this method, and this is very powerful. What we have seen is very powerful because this is nothing but the no solution case is nothing but our linear regression that we do. So when we say linear regression, right? So the idea of linear regression is this: you are given a set of points. Now I need to fit a line that passes through all the points. But definitely, right? I cannot pass through all the points. There will always be some error associated with the point, right? So let's say this is the line. A line is defined by its slope and intercept. So the equation of a line is y equal to mx plus c. And my goal is to find a line that passes through all the points. But since it is impossible, I'll find a line that the best line that minimizes the error. So what is the error in this case? So in this particular case, right? So what is y1? Y1 is nothing but this is x1. Okay, this is x1. mx1 plus c plus this distance. So mx plus 1c is this value. So mx1 plus c is this point. Plus error will give me, plus error 1 will give me this value, this point. Right? Similarly, y2. Y2 I can give it, y2 is nothing but mx2 plus c plus e2. So I can in general I can write y1 equal to mx1 plus c plus e1, y2 mx2 plus c plus e2, etc. y8 mx8 plus c plus e8, and this can be easily converted into this the earlier format we have seen. So here you have y. Here you have I can take m and c, right? M and c outside. So I have x vector plus some error vector. So this is of the earlier format, right? Definitely this is definitely there is no line that passes through all the points. So y equal to, so I will write it as ax cap to make that consistent with what we have previously mentioned. So definitely I cannot find y equal to ax. That is y. This is not possible. But I can always find y equal to ax cap plus error vector. So I can always find an x cap such that error is minimum. So this I can write it as y equal to ax cap plus b, and geometrically you can interpret in this particular way. So x cap will be A transpose A whole inverse A transpose phi. So what is x cap? In this example, x cap is nothing but slope and intercept. So basically what I'm trying to say is like I'm actually finding out the best slope and intercept. No? So that the error between the points and the line is minimized. So an entire linear regression can be seen from this point of view. So this can be seen as a homework, no? So now what if I add a extra column in this for this particular case, and which is nothing but the square of all the first column. So you can try it as a homework. What will happen? Now what if you add one more column, which is x cube, cubic raised to cube. So you can try and doing these experiments and see what happens now. What is the what kind of a graph that you get? You can see it as homework. But there are some practical challenges when you for you using this inverse, right? There's something called curse of dimensionality. In real world, right? We deal with matrices of size like 1 billion cos 1 billion, like so much big size. So the computing inverse, right? The complexities of the order O of n cube. So in order to avoid such problems, we go for matrix-free methods when we deal with high-dimensional data, especially when it comes to machine learning and all. We try to go for matrix-free methods, like gradient-based methods, and all we try to go for. But another problem that we have is like, when do we know we have to fit a line or we have to fit a curve? How do we know that? That's also a challenging problem. One thing that we can do is like we should have some domain knowledge. From domain knowledge, we can attack like whether to use a linear curve, linear or a non-linear, or a polynomial regression kind of a thing, linear curve. So another thing is to purely based on data. There are several data-driven methods of finding out which is the best fit curve. So this is the practical challenges. So this has several powerful application in like prediction, denoising, system identification, estimating missing data. So I would suggest to read up this work of Ivan Selesnik. So like he has done a wonderful work in signal processing, like so much in a very fundamental work, and you can see his work. And so now, yeah, I have limited time. So I'll talk about the 4 fundamental subspaces. So we have looked about column space, and we have also mentioned about row space. There is something called left null space and right null space. So let us start with right null space. Right null space, right? So we just defined represented as n of a. This is nothing but a set of all vectors x such that a times x vector equal to 0. The set of all vectors. So yeah, set of all vectors such that a times x equal to 0. So when I say a times x, right, you can see that. So when this is a, let me call this as a. This is a matrix. Row 1, row 2, row 3, etc. And this is my x. And this is 0. So when I say ax equal to 0 and say and x is an element of null space, like the set of all x that satisfies ax equal to 0, this x is orthogonal to the rows, right? X is orthogonal to the rows, right? Rows of a. That means the right null space of a, right? The right null space of a is orthogonal to the row space. So right null space is orthogonal to the row space. Similarly, I can say for the column space also. Like now let us say the column space, right? Column 1, column 2, column 3, etc. So I'll talk about something called left null space. I pre-multiply by a x transpose. No, x transpose a equal to 0 vector. So it is 1 cross n, 1 cross m. Let's say m. This is m cross n, and it is 1 cross n. So the left null space is the set of all vectors x such that x transpose a is equal to 0. So that means x transpose, the left null space is orthogonal to the column vectors. That means the left null space is orthogonal to the column space. So and that goes to the fundamental theorem of linear algebra. So I will not be able to cover this thing in this lecture, but I would suggest that this is one of the important theorems in linear algebra, like the fundamental theorem of arithmetic, right? Like that, the fundamental theorem of linear algebra, very, very important theorem of linear algebra. And you can say that the right null space, you can see here, the right null space is the orthogonal complement of the row space. The left null space is the orthogonal complement of the column space. So yeah, I will not be able to cover this at this particular point of time, but you can read more about it. And a course in this a course on linear algebra will definitely cover all these things. So now, so what we try to do in this lecture is we try to connect ideas. So like, for example, when I was in school and my engineering, right, I didn't see, there is no connection between ideas, right? Everything seems to be independent to each other. Like determinant is different from eigenvectors, different from solution to linear system of equations. There was no connection. But what we try to do today is like connecting ideas. Of course, I didn't say talk about rank. I think I would give this as a homework. You can read about it and how to connect new ideas. So what we did today is like we tried to connect invertibility with determinant with linear dependence and independence. Then eigenvalue. What do you mean by when eigenvalue is 0? Then we tried to connect with like solution to system of linear equation. I'm pretty much sure that there are so many connections. You can have so many connections, and it is worth spending time on this. So and I would like to end by saying this by telling something called do we know everything about y equal to x, right? So till 2004, right, in the field of signal processing, this Shannon and Nyquist, they are the one of the giants in the field of signal processing information theory. So there is something called Nyquist-Shannon sampling theorem. So for a band limited signal, the number of samples, right? The number of samples we take should be at least greater than or equal to maximum frequency. Like the sampling frequency is at least greater than or equal to the maximum frequency. So I have to reconstruct the signal. For reconstruction, the number of samples to be taken in 1 second should be at least greater than or equal to the maximum frequency. For example, if you have sine 2 pi 100t, the frequency in this case is 100, right? 100, right? So the sampling frequency should be at least greater than or equal to 200. So in 1 second, at least 200 samples has to be taken. So and it is followed like a religion. This has followed like a religion. Like nobody questioned it. And in 2004, right, Terence Tao, Immanuel Candice, and so David Donahoe and Justin Romberg, their work on compressed sensing has opened a new field that revolutionized the entire signal processing society. So now they say that you don't actually need to follow the Shannon-Nyquist sampling theorem. With limited samples, you can actually reconstruct back the signal, provided there are some conditions, provided there are some assumptions about sparsity. But that was an entire thing boils about y equal to x. So what I'm trying to say is that there's always a scope for fundamental research. There are always something new we can say about y equal to x. Y equal to x. So with this, I would like to conclude. So there are some interesting materials like Gilbert Strang's lecture, and he has a book called Introduction to Linear Algebra. It's a very, very good book, and I would definitely recommend his book. And also this book by Howard Anton. There are many theorems, many theorems and proof is there in the book Elementary Linear Algebra by Howard Anton. And there are applications of linear algebra, especially in like machine learning, deep learning. This book covered by Gilbert Strang. And there is also something called dynamic mode decomposition. Which is used in time series modeling, forecasting, prediction, and all. And it is nothing but fully linear algebra, like PCA, SVD. And there are some nice tutorials on linear algebra. So I will be sharing these like slides with Vinay. So yeah, so I think I can now take some questions and like suggestions, whatever. I will stop my presentation. If you have any question, you can ask. I know there are a lot of materials I couldn't cover completely, but this is just an introductory lecture. I think we have to go back and solve the problems diligently so that then only we can internalize the knowledge. So yeah, let us go back to the question and answer session. If you have any questions, you can ask.
Does anybody have any?
Hello.
Yeah.
So I always had this doubt. There are some matrices in which there are equal eigenvalues, but we get different eigenvectors.
Okay. Yeah.
For example, identity matrix, it has eigenvalues 1, 1, but its eigenvectors are 1, 0, 0, 1. I always found this kind of hard to, grasp. Can you like talk about that?
Yeah. See, actually, there are infinite number of eigenvectors. Eigenvectors are not unique, It has infinite number of eigenvectors, right? So let us take the identity matrix itself, right? See, for identity matrix, any vector is an eigenvector. See, any vector, you take, right?
Yeah.
It's an eigenvector. So basically, the direction is always the same. So, for example, x equal to lambda x, right? I can create a vector x such as it is 2x, Again, the scaled version of x I can create, right? So eigenvectors are not unique. Like there are infinitely number of eigenvectors.
Okay. Yeah.
But best example is the one that you actually mentioned, the identity matrix. All vectors are actually eigenvectors. like any vector, you like let's say eigenmatrix multiply by 2 1, you'll get 2 1. So, yeah. And but one more thing is important, right? So see, when you have same eigenvalues, correct, nothing, fine, yeah.
That's it. Yeah, thank you.
Yeah.
Any other questions? Also, please fill the feedback form. It will help the instructor to get a feedback of how the lecture was, as well as for us to gauge what events to have in the future. We'll wait for a couple more minutes if anybody has any questions.
Yeah.
So there are 2 other lectures in the afternoon. One is at 2 o'clock and the other one is at 4. The 2 o'clock one is on probability, which will be taken by Sahasranand. And the 4 o'clock one is on differential equations, which will be taken by Professor T. Srinivas.
Excuse me, will you be sharing these slides? Possibly, is
Yes.
it possible, so that we can read it later?
Yeah, definitely. I will be sharing that slides.
Yes.
Okay.
So
yeah.
Please fill the feedback form for that. So we'll put it up on the website, or if that is not possible, we'll actually share it with those who have filled the feedback form. So please give your email ID there as well when you're filling it. Okay, so I guess there are no more questions. So if possible, if some of you can, okay, is there a way to do that? Okay, if some of you can unmute yourself and share your video, probably it will be nice to capture a screenshot of this before we proceed. Can some of you please, yeah, thank you. A couple more at least. Yeah, all right. Thank you. Yeah, so thanks for attending this lecture. Thanks Harikrishnan for the wonderful lecture. So we surely know how to make good coffee now, I hope. So yeah, so others please join for the other lectures in the afternoon. Thanks Harikrishnan.
Yeah, thank you for this opportunity, Vinay. Yeah, thank you. And Sahasranand also for suggesting my name.
Yes.
Thank you very much. It's a great learning experience for me. I really enjoyed preparing for this lecture. Yeah. Thank you.
Okay. Yeah, so we'll end this session now and we'll convene again at 2 o'clock. Yes.